This week we're going to be talking about statics, mechanical advantage, pivot points, equilibrium, all the things that kind of go into understanding statics. And sometimes I talk about statics as a Shakespeare play, Much Ado About Nothing. And we'll get to what I mean by that as we go through this. So the first thing is static equilibrium. What is static equilibrium? Well, it really means nothing is moving. And in static equilibrium, in translational equilibrium, the sum of the forces equals zero. So if I stand here and I'm standing still, all the forces are balanced, the force from the floor, the force from each of my feet, everything's balanced. I am in static equilibrium. This can also be true when you're in motion. And this is the part most people don't get. If I am in motion but not accelerating, then I am in static equilibrium. A great example of this would be a skydiver who has reached terminal velocity. Once you've reached terminal velocity, all of the forces on you are balanced. Now what this means is a skydiver can actually make subtle changes to the forces on them, and they can drift around and do different things, but they're in static equilibrium while they're just falling, free falling straight down at constant velocity, until of course they get to the ground and then things change dramatically. The other part of equilibrium is rotational equilibrium. So it's not enough to simply be in translational equilibrium where you're not moving side to side, or because you could be spinning. Now, if you're spinning at a constant rate with constant angular velocity, again, you're in equilibrium. But if you're accelerating in any way whatsoever, you're very much not in equilibrium. So we have two basic things to reach a state of equilibrium. They are the sum of all forces equals zero. And we use this capital sigma to indicate sum. And the sum of all torques equal zero. This is why I call statics much ado about nothing, because your goal in reaching static equilibrium is to add everything up to zero. You want all the forces to be zero. You want all the torques to be zero. And you're like, wait, if all the forces are zero, the torques are going to be zero too. No, that's not true. All right? Because this, I'm supporting the weight, I could be supporting the weight of this on one finger, except that the torques are not zero and it wants to rotate, right? So you have to have both the force and the torque equal to zero. And again, this is a capital sigma. You're familiar with that from fraternities and sororities probably. That's a capital sigma. We use it to indicate sum. This is a lowercase tau. I wrote tau with a tau. It's a lowercase tau. And that is our symbol for torque, as you knew from last week. All right, that's it about equilibrium and getting to equilibrium. Again, sum of the forces equal to zero, sum of the torques equal to zero.